Okay, thank you so much. I really appreciate the opportunity to speak today. I thank you for to the organizers for giving me this opportunity. What I want to talk about is actually a really good follow-on from what Clive just presented, and there's a lot of synergy in what both of us are going to be asking for and pointing out. So right now we are, there we go. Right now, we are at this amazing turning point to be living through. It's chaotic. There's a lot of uncertainty. I mean, the Viper cancellation is a really good example of the massive uncertainty that we're living with. But as somebody who has devoured space science fiction since early years, I am amazed at the opportunity to be living in a time when we may actually see humans living on the moon and existing on the moon and moving on to Mars. This is a really exciting time to be alive. But at the same time, as a scientist, I find myself feeling alarmed at the pace and at the path that we might be taking. So something that I want to talk about is a way to do this so that we don't permanently lose the scientific value of lunar volatiles. These are a non-renewable resource, not just as a resource, but scientifically. So how do we know the scientific value of lunar volatiles? There have been several references recently to Origins, Worlds, and Life, the most recent planetary science decadal survey. This decadal survey is a community consensus for what the priorities are for the next decade. And we know that it's a community consensus because of the numbers that you look at associated with it. The decadal survey included inputs from more than 500 white papers internationally submitted. There were 153 panel and 23 steering group meetings over a period of a year that went into defining this document. And more than 300 presentations were invited to be given by external speakers in open sessions. So every effort was made to ensure that this document is the consensus for the community. And one of the most valuable things that came out of it were 12 chapters that outlined science questions that were the top priority for the next decade. And what I'm going to go through is some of the questions that the composition of lunar volatiles, actually getting those measurements, could contribute towards answering. So starting with the first questions, the initial conditions and the building block formation when the solar system was forming. We want to understand, particularly ices, what the composition was as a function of distance from the sun. That's something we have models that predict, but there's different models that show different things and don't fully agree. Ground truth data is going to be really important for helping us to understand this distribution of volatiles when the planets were forming. With the giant planets, when they formed, we have a pretty good expectation that they migrated after formation, but we don't really know when or how they migrated. Some models show one thing and others models show another. For example, this model on the top right here suggested that Jupiter migrated inward at first, and then after Saturn formed, it started migrating inward as well and pulled the two back, which is really groundbreaking for us because the Earth and Venus and Mars could have been ejected from the solar system had Jupiter continued to move inward. So we're alive today because of that. On the other hand, there are models that don't suggest that Jupiter migrated inward, but they show that maybe Uranus and Neptune traded places. And these are just two examples of the wide variety of models for planet migration that match the existing data that we have available to us today. So we are data starved when it comes to understanding the formation and migration of the giant planets and the implications for Earth. So moving onward, that gets to water and delivery of volatiles to the inner planets. The migration of the giant planets allowed the scattering of small icy bodies and small water-rich bodies inward to impact the Earth, Venus, and Mars and deliver water and other volatiles. Now, we do know that some volatiles came from our initial formation, but we don't know how much of it came from initial formation, how much came from comets, and how much came from asteroids. And the composition of volatiles on the moon could be really important for that because the delivery to the Earth-Moon system is the same. And what was delivered to Earth is mixed in with our atmosphere now. What was delivered to the moon could be stored in the permanently shaded regions. And then there's just the impact on the entire structure of the solar system. We want to understand how solid bodies evolve in their interior and the resulting composition of the solid bodies. I'm showing here on the left an illustration of the moon when it might have been volcanically active, and then on the right, an image of Io, because a lot of times when we study the moon, we look at the volcanic features on the surface, which are amazing because these ancient volcanic features on the Earth have been covered by biomass and there's been water. So with the moon, we have the ability to study ancient volcanic processes without the interference of what is happening on Earth. That's really important because we like being alive. But the other aspect of volcanic activity, though, and that's why I have an image of Io on the right, is that volcanic activity releases volatiles from the interior. The composition of these volatiles that were released are a tracer of the formation processes for the moon and the Earth-Moon system, and for the history of the moon. And it's possible that deeper within the PSRs, there may be ancient volcanic volatiles stored there. We don't know if that's the case. We don't know how deep they would be, but it's really important to measure the composition of the volatiles that are there, and test whether they have volcanic origin. There also is gas that is coming from either the interior or just the crust in the exosphere today. So the moon's exosphere has not just traces of external activity that's delivering volatiles, but it also has endogenic gases that we haven't measured the composition of. There were some Apollo measurements that got some composition, but it was very limited. And all of the activity of robotic missions and eventually human missions are going to create an anthropogenic exosphere. And this is just the nature of our activity. So what is really important and what is kind of alarming to me and essential is that we really need to make a concerted effort right now to characterize the volatiles that are coming from the interior while we still can measure them, and before we wash them out with our own volatiles that we're bringing with us. And finally, everything that we learn from the volatiles on the moon will have implications for our ability to understand the bigger picture of what we're observing outside of the solar system. We have observed hundreds and thousands of exoplanet systems, and we haven't really found an equivalent of our own system, mostly because of detection limits. But the diversity of system architectures that we're able to find is amazing. And so understanding how our system originated, formed, and got to where we are helps us to understand better what we're seeing outside of our own solar system. So what measurements do we need? We need composition. A lot of the observations that we have been doing of the moon have been limited to water because of the ability to detect hydrogen and because it's the one that we can have access to, particularly through remote methods. The L-Cross experiment provided more than just water. It provided us with composition with carbon and nitrogen and sulfur-bearing species and oxygen as well. And that composition is extremely valuable. What we could also use is noble gases, because noble gases are not reactive and they can provide a really valuable tracer for formation materials and for evolution of materials. And then finally, we need isotope ratios. We need the isotope ratios of the noble gases and then isotopes of carbon, nitrogen, hydrogen, and oxygen. All of these measurements will help us to better understand these questions that have been posed by the decadal survey. Now, getting from the measurements in the PSRs, if we are able to get very detailed composition measurements of PSRs and of the exosphere, tracing that back to the origin of these materials is very complicated, because when materials are delivered to the moon, they don't end up stored in the permanently shaded regions in their pristine composition. They go through a lot of processes, and I'm showing many here. So it seems like a really big challenge to get all this data and then try and get some science value out of it. But the truth is that it can be solved. We have developed a very simple model that relied on elemental composition and were able to trace the L-cross composition back to a cometary origin. And this is a very simple model. Others could use it as well. It's something that is possible. It can be solved if we get the composition. We just need these measurements before we change the volatiles or reuse them for something else in order to ensure that we get the scientific value out of what is on the moon today. So what we need, and following on Clyde's call for international collaboration, we need an international strategy that ensures that we get this great science return from lunar volatiles. And there are really three components that are important for achieving this. First of all, partnerships between scientists and anybody who is going to the moon. People who are going, if you're sending a lander to the moon, if you're sending people to the moon, there needs to be a partnership with scientists. And there's a lot of this that's already happening. We need lunar volatile experts, and there are dozens across the world who are interested in playing a role in this, but we need lunar volatile experts involved in activity on the surface of the moon. Also, anywhere we go on the moon, we need to be able to measure the composition of the volatiles where we are, the pristine volatiles, so that we don't lose that opportunity. And I'm not the PI of any instrument proposal. I'm not even a co-I on any instrument proposal right now. But what I would really like to see is mass spectrometers all over the moon, because they can get the noble gases, they can get isotope ratios, and they are extremely valuable for the composition of lunar volatiles. So I'm making this call as somebody not trying to sell my own instrument, but begging for the science data that we need. And again, like Clive was saying, we need data. We need the data to be available. And so none of this, the first 2 points are useless unless we have a commitment to public sharing of observations by everyone who is going to the moon. So this is very important that and this is something that worries me about the Viper mission. If we get picked up by a partner and that partner decides to own the data, then the data may be for sale instead of the spirit of NASA's approach to missions of making our data available to the public for the public good. So I hope that whatever happens with Viper, if it does fly, the data is made publicly available. And I will finish with that. Thank you.